Alright, so 4.3 derivatives and the shapes of graphs. Pretty intuitive, pretty logical here, so we'll get through. So what does f prime say about f? Well, f prime tells us the direction in which the function is heading. If f prime is positive, that means the function is increasing. If f prime is negative, that means the function is decreasing. That goes back to algebra 1, algebra 2, logical slope stuff. So yeah. Um, F double prime tells us the bending. We'll get to that later. I'm not going to cover that now because it's something with concavity. So yeah. So why does the sign of f of prime of x matter? Well, I don't think they do the proof in the book, but I'll do so here. So remember that I think it's Fermat's theorem. Fermat's theorem says that at I'm gonna say x for extrema, f prime of c is equal to 0, which is logical. So we'll take three cases in which f prime of c is equal to 0, and the first case, it's a constant derivative all throughout, meaning that this function is constant. So constant such that f prime of c is equal to 0. Here we have 0, f prime of c is equal to 0, and we know that the derivative is positive all throughout. So it's that point and the negative all throughout. So negative, negative, and positive, positive for this last one, where f prime of c is equal to 0. Well, in what world would this case yield a maximum? The function is going down, and then it starts going up from a point. If that's the case, then if it's going down, how can that ever be a maximum? There'll always be a point higher than this. So this means that this is minimum and this is maximum. So the logic is simple. If the sign changes from positive to negative, it's a maximum, and it changes from negative to positive, that's a minimum. You can also use logic to figure that out. So that's the first derivative test. Now, the first derivative test is great because you can use the first derivative test to find maximum and minimum, or if it's neither. And in the case that it's neither, the signs don't change. So usually it'll be like a function like this, like x cubed or something. It'll be positive, 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 and go 0, 0, 0, 0, and then negative, and then positive, positive, positive. No way does f ever fall below 0, or f prime ever fall below 0. So in that case, this function is a positive. And in this case, this function has no maximum or extrema at this critical point, which I guess would be an interval of critical points, but the logic is still the same. So the increasing decreasing test is simple. I have it in the slides, but I'm just going to write it out again. If f prime of x is equal to, or is greater than 0, then f is increasing, which I literally don't know why they say this because it's the most obvious thing I've ever heard. But I guess for math they have to establish the theorems, and it's increasing. Maybe I should type this out because I'm a lot faster typer than I am a writer. So let's do a practice problem. The practice problem is going to be quite simple. Let's take a function. F is equal to 3x to the fourth minus 4x cubed minus 7x squared plus 5. Well, what is f prime? To establish critical points, that's going to be equal to 12x cubed minus 12x squared minus 14x plus 5. And here we can factor out a 12x. And, oh wait, sorry, and no 5 at the end, actually. Yeah, hold on 1 second. Oh, sorry, I meant 12x. My handwriting is pretty bad on my notebook, so so minus 12x such that this becomes minus 24x. So logical stuff here. So now what we're going to do is we're going to factor the 12x so we can get it to quadratic and factor it even further. Like that. And that becomes 12x, x minus 2, x minus 1. X plus 1, I mean. So at critical points, or for any function, I don't know if the name of the theorem, but if the function is equal to 0, the input that makes it equal to 0 are the only points in which sign changes can occur, which are quite logical because it has to hit 0 then fall below. So in what cases is this derivative equal to 0? We have x equals 0, 2, and negative 1. So if these are the only places sign changes can occur, let's draw it out. We have 0, negative 1, and 2. If we let's plug in a number below this line, and we'll do something like negative 2. Well, if you did so here, this entire term would equal 4 plus 2, 6. This would be equal to 4, and that would be equal to negative. So it would be negative here. Now let's try a number past negative 1, and we'll do negative 0.5. Or something simple, actually. Maybe, yeah, negative 0.5 might be the simplest here. So negative 0.5 here, that would equal 0.25. So this would be negative, negative, and be positive here. Could plug in 1 here. That's going to be negative here, and 2 onwards it's going to be positive. So the intervals of increase are going to be equal to where the derivative is positive, and the derivative is positive from 2 onwards. So we'll do to infinity. And also you can do, oh sorry, I did a close bracket for infinity. That's not correct, but I fixed it. And decrease would be wherever it's negative. Oh, actually, this should also be a negative 1 to 0, unity to 2 to infinity, and decrease would be negative infinity to negative 1, and union 0 to 2. And since it's intervals, you don't have to do bounded or whatever. So now we get to the first derivative test, and I've already explained that before, but the positive and negative sign changes. So if f prime goes positive to negative, it's a max, which is logical because it has to reach that high point first before switching to f prime is equal to 0. And f prime goes negative to positive, min. So yeah, if f prime does not change, it's neither a max or minimum. Also, if f prime of c is defined, then f prime or f of c has to be defined as well through derivative principles, which we know here. So let's do another problem, and it's gonna say, let me type this out because I am a lot faster typer. X plus 2 sine x squared inclusive. Inclusive just means it includes the points. So what do we know? Well, first we'll have to differentiate the function, and by doing so, we get g prime, or sorry, f prime is equal to 1 plus 2 cosine x. Logical stuff here. And now we find the critical points. Now, I can do this logically, but my teacher did it algebraically, but, you know, I can probably solve it a lot quicker without the unit circle visualization. So cosine x equals negative 0.5, and that would be when it's 45 degrees. Not 45 degrees. That would be when it's 60 degrees. So essentially when cosine is equal to when x is equal to negative 0.5, which is going to be on the left side of the unit circle, which is going to be pi over third. So that would be equal to around 120 degrees, which is equal to 2 pi over thirds. There we go. Wait, 2 pi over thirds. Yeah, 2 pi over thirds. Yep, 2 pi over thirds is correct. So that would be one of the maximas. Or not maximas, that would be one of the critical points. And we also know that x is between 0 and 2 pi, which means that we also have to include this bottom point here. And that's just going to be 360 minus this point, which is, or 2 pi minus that point, which is just going to be equal to 4 thirds pi. 4 pi over thirds, which is logical here. So now since we have the entire critical point chart, we can use the first derivative test. And the first derivative test just states what I said before. Oh, sorry, I shouldn't write that. Shouldn't write the answer down before I give it to you. So we have 2 pi over thirds and 4 pi over thirds. on this number line and 0 right here. So let's test the number before 2 pi over thirds. And actually, I could probably just use logic to figure this out. Um, cosine is positive throughout this entire interval. And the adjacent shrinks here. So this all has to be positive. And you can test a number between here. You could probably test pi in this case. So let's put pi in. That would just equal 0 at the most. Yeah, that would just equal 0 with 2 pi right here. Also 2 pi as well. Yeah. So that means this interval will be negative here. Because negative 0.5 between these, the closer you get to pi, the greater the negative magnitude becomes, which makes that negative or plus. I know it sounds like buzzwords, but you can just plug in a number from each interval because critical points are the only places in which the sign changes can occur. So negative, negative, positive, positive. So if we switch from positive to negative, there's a max here and a min here. So we get that 2 pi over thirds equals max, and 4 pi over thirds equals min. So that's logical and pretty simple. But now we get to concavity, and concavity is it could be a hard concept to grasp. So we have concave up, which essentially means that f double prime is equal to 0 or greater than 0, which means that the slope is getting more positive. And this is logical. If you take the slope between these 2 points, and you take the slope between these 2 points, I would argue that this slope is steeper than this slope, which is great logical because f double prime is how fast f prime is changing. So f double prime is how fast f prime is changing. Then if f double prime is increasing, then it's going from a small positive to a greater positive and getting a greater slope, so on and so forth. And the same logic applies with concave down. The slope is decreasing, so you'll see something like this. Or actually, let's do it like this. We'll keep it that f prime is positive for the most part. So f prime is positive here because the function is increasing on this entire interval. But we see here that it's getting a lot less steeper and less steep because during this interval, m2 is less. M1 is greater than M2. So that's the logic there. And here I just use positive things to illustrate. But the theorem goes as this. If f prime is positive, then it's concave up. If f prime is negative, then it's concave down. So that's logical. That's easy. So yeah, we'll go on to the next one. Well, we'll go to the second derivative test. And the second derivative test, also note that it's not always going to be a major change or a very, very smooth curve or a very, very steep curve. All that means is it kind of curves as it goes along, like the teapot as mentioned before. So suppose f prime is continuous near C. So this is the second derivative test. So we just need continuity for C technically, but it says is caught near C to include the points near C. So if f double prime equals 0, then that means f prime is constant, which means it will be a linear function, theoretically. But if C is equal to all x, I guess, what I'm saying. Well, anyways, we'll move on. So if f prime of C is equal to 0, and f double prime of C is equal to 0, then f has a local minimum or maximum. Or, sorry, f has a local minimum, or it could be also absolute maximum, or absolute minimum in this case. And if f prime of C is equal to 0, and f prime of C is or less than 0, and greater than 0 here. Oh, wait, no. It would be, oh my gosh, less than 0 and greater than 0, then, oh, wait. No, negative. positive, then um, f has a local maximum, which is logical to conclude. And it's the same thing as it's the same logic as the first derivative test. Let's take the first case, for example. If f prime of c equals 0, that means it's a contender for a max or min. And f double prime of c is greater than 0, then let's look at the graph. That would mean that the slope is curving upwards. Um, so if it's going from so if it's 0 right here, it had to hit 0 somehow. And if f double prime of c is greater than 0, then if it was positive, then it would look something like this, because it's positive here, and then the slope keeps increasing continuously. So it would probably look something like that, like a teacup shape. But if it's negative, and f prime of c is greater than 0, then that is the only case in which a local maxima can occur, or a local minima could occur, because f double prime of c indicates that it's switching the f double prime of c from a negative to a positive magnitude, or from a positive to an even greater magnitude. And because f prime of c is equal to 0, and this is positive, then this negative slope this slope cannot be positive, because if it was positive, it would never hit 0, because if you're adding a positive number, or adding a positive to a positive just makes it more positive, and will never hit 0. So that means this function had to be negative beforehand, such that f prime of c has to equal 0. So that's the logic here, and the same logic is there. So it's the same exact logic. I mean, technically you can use the first derivative test, but some people say the second derivative test is easier. So we'll do a practice problem here, and this is all just theory, so let's put it into application. Well, I guess this would also be theoretical, but so yeah. Well, let's discuss Kant, or continuity, points of inflection. Local extrema. And let's sketch the curve. Well, it's a polynomial, so we know it's continuous everywhere. It's number one. Points of inflection are simply where f double prime of x is equal to 0. And local extrema and local maxima will be something different, which we'll solve right now. So first we have to differentiate the function, and we get 4x cubed minus 12x squared, which we can factor out of 4x squared from to get x minus 3. So now we know the critical points, which is x equals 0 and x equals 3. One second. Yeah, x equals 0 and x equals 3. Alright, so first let's find the local minima and maxima. Sorry. We'll draw a number now. Since 0 is here, let's just say that that's -1, 0, that's 3. It's x equals 3, by the way. And let's say that this, it doesn't matter actually what's past that, because sign changes can only occur at these points where f of x is equal to 0. Well, let's try the first case. And also, it works when it's also undefined as well. But that's a different topic, I guess. So let's start from x equals 0. And let's take a point right here, which is going to be -1/2. If we plug the -1/2 here, this would be just negative. So now let's plug in 1. And I like this interval from 0 to any number greater than 1, because you can just use 1, and it makes things so much simpler. And that's going to be negative as well. So that means there is no minima or maxima here. And we'll do it again. And we'll choose 4, and that becomes positive, because this term is always going to be positive, and this 4 minus 3 is equal to greater than 0. So they're both positive. So that means only a minima occurs here, because it goes from negative to positive. So yeah, we just use the first derivative test. In fact, I don't even know why they use the second derivative test. Probably for other theories and applications, but there we go. Now let's get to the points of inflection. And remember that the points of inflection are just the same thing, except we differentiate twice. I think it was 4x cubed. And we get 4x cubed minus 12x squared. Factor out the 4x. Or actually, if we could factor 4x squared minus 3. Actually, why would I make this a product? Let's just differentiate once more to get f double prime. F double prime is equal to 12x squared minus 24x. Factor out of 12x to get x minus 2. So we know critical points for f prime would be these two, or that the points of inflection would be 0, 2 for these points. Well, actually, we don't know if they're we don't know if the sign changes occur there, but we'll check here. So again, we can just do 2, 0. I love this interval, again, because you could just choose 1, and we'll do -4, or something like that. I guess you could put negative infinity as well. So we'll test from 0 and before, and we'll do a number like -1, which makes things simple again. That would be negative, and that would be negative, which makes this entire interval a positive. Test from 0 to 2. Let's choose 1. It'd be negative, 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 because negative, positive. So yeah, and then from 2 to infinity, let's just use 3, and it's going to be positive, 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 positive. So that means from here, it would be, well, this entire interval is concave up, this entire interval is concave down, and this entire interval is concave up. And the points of inflection would be 0 and 2, where it changes. So we can also sketch the graph, and it would probably look something like this. Well, we'll use the critical points, so 0, or 1, 2, 3. And we know here that we can use the original number line, which we had from the first derivative test. And it'll probably look something like this, because we know that a maxima occurred at around x equals 3, I believe. So the logic is pretty simple and sound for that. So that's it for maxima, minimas, concavities, inflections. So